Hi, welcome to video number 1. Today's content comes from a lesson I recently taught, and it is about characterizing the multiplicative group of integers mod n. And in particular, let's see, I'm going to demonstrate that a, which is some integer, and then I'll put a bar over it to denote the equivalence class of a mod n, is invertible. Mod n, of course, if and only if it's co-prime to n. Okay, so it's an if and only if. That means there are two directions to prove. I will do the easy part first and show that if the GCD of a and n actually does equal 1, then a has a reciprocal mod n. And then I will do the slightly harder part and show that if a and n have a GCD greater than 1, if they have a non-trivial common factor, then a bar in particular can't have a reciprocal mod n. So I'll do the easy part first, like I said. In fact, I don't even have to erase this top part to do that. Okay, so we'll assume that GCD AN does equal 1. Okay, and now I'm going to use a theorem which follows from the correctness of the Euclidean algorithm, which says that there exist integers x and y such that xa plus yn equals 1. And then I will rearrange this equation to simply read xa equals, 1 minus yn. But I'll suggestively write it as 1 plus minus y, which is just some integer times n. And then it's clear that mod n, I'll use triple equals to denote equality mod n, this equals 1. After all, it's 1 plus some multiple of n. And therefore, thus, x bar, let's say, equals a bar inverse. In other words, x, or rather x bar, its equivalence class mod n, is the reciprocal of a. Okay, so that completes the first part. We've shown that this if is true, but the only if I will do by assuming that a and n have a common factor that's greater than 1, and then showing that there can't be a reciprocal for a bar mod n. Okay, let's do that. For that I will need more space, because that part is a little bit harder. So now we assume that GCD of a and n is some integer k, which is strictly greater than 1. All right, then let's see what we can say. Then I want to consider this equation, which is always going to be true in some sense, that n over k times a equals a over k times n. Of course, this is just true as an equation between rational numbers for any integers a, n, and k, but in particular when k is the GCD of a and n, or even any common divisor, n over k and a over k will be integers, and if as long as I treat these terms in parentheses as integers rather than rational numbers, then this is actually a perfectly good integer equation. And I want to use, let's see, what do I want to use? So I can use the fact that these are, I can use the fact that a over k is an integer. That only requires k to be any divisor of a, to show that this is some integer times n, and therefore this whole thing is 0 mod n. And so then I actually have this equation that n over k times a is 0. And I'm not being careful about distinguishing between integers and their equivalence classes mod n. I probably shouldn't have even drawn the overbars anywhere, because I'm not going to keep track of that distinction. It's really not necessary. Okay, now I need to use the fact that, let's see, I need to use the fact that k is greater than 1. So this is going to mean that I can say something about n over k. It's not 0, for sure. It's got to be positive because n is positive. We're looking at things mod n. And k is positive. It's the GCD of two integers. So this is certainly strictly greater than 0. But because k is greater than 1, it's also strictly less than n. So actually, n over k is going to be strictly between 0 and n. Okay, and now where do I use this? Right. Since n over k is not 0, this equation leads to just two cases. Case 1, a equals 0 mod n. If that's true, then a actually equals jn for some integer j. And if that's the case, then it's easy to see that we don't have a reciprocal. In fact, we don't even need that. If a had a reciprocal and was 0 mod n, then I would be able to write a inverse a has to equal 1, but that also has to equal a inverse 0. And of course, anything times 0 is 0. It's easy to see because if a equals jn, then when I multiply it by something, by a inverse in particular, a inverse a equals a inverse j times n, and so a inverse would have to be an integer. So a inverse j is an integer, so this whole thing is still an integer multiple of n. In other words, really no matter what I multiply a by, if it is in fact 0 mod n, I'll still get something 0 mod n. In particular, it can't have a reciprocal. So no reciprocal. I don't know if I said inverse or reciprocal earlier. It doesn't really matter. Case 2, a is a 0 divisor. That means a non-zero element, because I already handled the case where a was 0, which I can multiply by another non-zero element, and we know that n over k is not 0, to get 0. And 0 divisors can't have reciprocals either. After all, if we had that, I'll rewrite this as a n over k, I can multiply on the right. So if n over k a equals 0, if it did have a reciprocal, and I'm realizing now that maybe I didn't even need to do two cases, then I could multiply on the right by that reciprocal. A inverse would still be 0. After all, 0 a inverse is 0. And this has to equal n over k. That's what these two being inverses means. But we already ruled out the possibility that n over k was 0 mod n, because it's strictly between 0 and n. So 0 divisors, this is a very general fact, a 0 divisor in any ring can't possibly be a unit, can't possibly be invertible. So again, no reciprocal. And that is it. I have shown now, first of all, that if the GCD of a and n equals 1, a has a reciprocal, and I have now shown that if the GCD is greater than 1, there can't possibly be a reciprocal. So I've proven the original theorem. So we know now that z mod n z star, or times, or whatever, is exactly, as a set, is as a set, is the set of all a bar, so equivalence classes. That means that we're, in some sense, looking at things between 0 and n minus 1, such that a bar, I have to write GCD because I'm not using Dummett and Foote's notation with the parentheses, GCD, a bar n, In fact, I can just say an equals 1. Okay, I think that's a good place to stop. That was my first video, for better or worse.